All right, so we're in fourth period and we're recording notes, so if it's weird, sorry. Okay, today we're learning about hypothesis tests, but now we're dealing with numeric data, okay? So really quick, I just want to do a recall. I'm going to do it over here. And remember, back in the day when we were doing confidence intervals, we had choices to make. The first thing we have to decide is the data numeric or is it categorical? Well, we're dealing with the same situation now that we're doing tests. So if the data is categorical, cool, everything is perfectly fine. If it's categorical, we're great. We have a one prop Z test that we're running. If it's numeric, there are certain questions we have to ask ourselves. Does anyone remember those questions?
Sigma known or unknown.
Oh my goodness, yay. Sigma is either known or sigma is either unknown. And based off that fact, back in the day, we decided to do a Z interval or a T interval. Okay, similarly, if sigma's known, we're doing a Z test. And if sigma's unknown, we're doing a T test. That was just a little blast to the past. Now we're coming back to today, and we're working with these Z and T tests, okay, today. So honestly, okay. Alrighty, so the rules still apply for what we learned the other day, except for now we're basically replacing pi with mu, and things look very similar, okay? But there's a couple differences because we're dealing with numeric data today instead of categorical. Step one is still going to be that we define mu in words. So we define our parameter in words, and this time it's mu. Okay, step 2 and 3, remember they don't have to be in any particular order, but we're setting our mu equal to our hypothesized value. And then the alternate, we have 3 options. Either mu is less than that hypothesized value, it's greater than that hypothesized value, or we don't know, is just not equal to that hypothesized value. Okay, step 4 is check conditions. Okay, the conditions are very similar, actually the same, as those for a confidence interval. Condition number 1 is the sample random? Condition number 2 is the sample normal. I'm gonna let you guys catch up because we're gonna spend a minute on this normal situation. There are 3 ways to check normality now. So we already know 2, we're gonna add another one, okay? Way number 1 is the best way. And this is if the population is stated as normal, then the sample is also normal. So it is normal. Okay, but that doesn't happen all the time. So then we have like a second way. And that is if n is greater than 30 by the central limit theorem, then the sample is approximately, and that word matters, normal. And now here's our new way. It's pretty simple. It's not wild or anything. There is a way, and this is if you're given raw data, but less than 30 data points. Then, instead of just giving up and being like, we don't know, you can make something called a normality plot. And we're not going to get too into, what goes into a normality plot or anything like that right now. Let's just take it at face value. And you can create a normality plot. And if that is approximately linear, then it's safe for us to assume the distribution or the sample is approximately normal. How you make a normality plot is, we'll be doing an example on Monday with this. Your homework doesn't have it tonight, so don't worry too much about it. I'll make sure we go over it on your quiz review. But we go to second stat plot, like just as if you were gonna make a scatter plot or anything like that. And under where it says graph type, there's those 3 little boxes. Just kidding, 6 little boxes. It's this one. All right, so there's our 3 ways of assessing normality. Okay. Step C, sigma's either known or unknown. And D, since we're dealing with a large sample test, N needs to be less than 10% of that population. Okay. Step 5, same as normal, set alpha. And it's the same as before. Either it's going to be given to you, you have to look at the context of the problem because you're asked to analyze type 1 and 2 error, or when in doubt, alpha equals 0.05, move on with your life. That's it. Okay. Step 6. We need to state the test and write the formula. All right, if sigma's known, then we're running a z-test. And our formula is just the z formula, except for we're going to be using the sample mean as the x bar, sigma over root n. And if sigma's unknown, then we're running a t-test. Okay, what's the one thing that changes from this equation to this equation? Sigma changes into S. Yay, okay. So x bar minus mu over S over the square root of n. We're almost done. All right, in step 7, you're gonna find that value, whether it's z or it's t. And then step 8, you're gonna find the p-value. And you're gonna compare it to alpha. Thank you. All right, remember in step 8, your probability statement has to match whatever's going on in step 3, okay? So if in step 3, okay, If in step 3 you said less than, in step 8, your probability statement of Z or T and the value you use from step 7 is going to go in here. You also say less than. If in step 3 you said greater than, we're looking at the probability of that Z or T that you got from step 7 being greater than. And if you said not equal to, then you're looking at the Z value from step 7. If that Z-score comes out negative, we're looking less. If that Z-score comes out positive, we're looking more. And what do I have to do? What has to be done? Times 2. And then we compare to alpha, okay? If the p-value is less than or equal to alpha, we reject that null. If it's greater than alpha, we fail to reject and keep the original claim. And step 9 is an in-context conclusion. We should. Okay. We can, we'll see. All right, example 1. Here we go. Water bottles are supposed to be filled with a mean of 16.9 ounces and follow a normal distribution. That's helpful information. The manufacturer wants to check the machine filling the bottles to see if it needs repairs. They take a simple random sample of 10 bottles and get a mean of 16.4 with a standard deviation of 0.2 ounces. All right, let's just start off. First things first, let's define our parameter, which is mu. And this is the true mean. And then I ask myself what? And in this case, it's, amount of water being filled into the bottles, but I'm not writing all that. Amount of water in bottles in ounces. That'll work. And then I'm going to set up my null and my alternate hypotheses. Just get them ready. And then after that, I'm going to go digging through the problem to look at all the provided information to see what's helpful or not. It's okay if the video has long silent things because you can just watch it and pretend you're really in 4th period, right?
Yeah, I guess.
That's fine.
Do you get these examples from the book?
I get a little from here and a little from there. Sometimes from the book, sometimes from worksheets, sometimes from workshops. Sometimes from my own AP stats material that I took in high school. I have some of that still,
Really?
so really. Okay. Let's go in and check out all this, see what's going on here. Okay. Water bottles are supposed to be filled with a mean of 16.9 ounces. What is that? The null. Yeah, that's mu. Nice. Okay, let's keep digging here. The manufacturer wants to check the machine filling the bottles to see if it needs repairs. They take a simple random sample of 10 bottles. What's that? N equals 10. Okay, and they get a mean of 16.4. What's that? X bar is 16.4. Here's the good $1 million question. With the standard deviation of 0.2. What's that? S. Not sigma because it comes from a sample of 10. That's where that standard deviation is calculated, okay? Cool. Now I have it set up, but I need to decide about my alternate, okay? I want to know if the machine needs repairs. I don't necessarily care if it's less or more. I just want it to be operating correctly. So what is my alternate? Not equal. Cool. Let's keep going. Step 4, check conditions. Is it random? It says SRS over here, so that's stated. Nice. Okay. Step B, is it normal? It said up here follows a normal distribution, so it's stated. Yay. Step C, is sigma known or unknown?
Unknown.
Nice. Because I know S, not sigma. And D, 10 has to be less than 10% of that population. Okay. As far as alpha goes, there don't really seem to be any like major, huge life or death consequences here, and I'm not asked to analyze them, and I'm not given an alpha value, so alpha is 0.05. That's fine, and I'm going to move on with my life. That works out. Step 6, name the test. What type of test? T-test. And the formula, T equals X bar minus mu over S over the square root of N. Okay. Step 7, let's calculate that T value. T is equal to X bar, which is 16.4, minus mu, which is 16.9, over S, which is 0.2, divided by the square root of N, which is 10. And if you guys are okay with it, I'm pretty sure we can all do this in your calculator, and I'm just going to be the calculator today. And this is going to be negative 7.906. Alrighty. Step 8, this is where I'm going to ask questions that I'm a little bit scared to ask, but it's okay. We will remember back to these things, okay? So, my T value is negative. And normally, step 8 and step 3 need to match, but this is a not equal to, and I cannot write not equal to over here. That's illegal, cannot happen. What sign goes here? Less than. Why? Beautiful. Since the t-score or z-score is less than, sorry, I'm going to drag it up a little bit, right here. Since the z-score is negative, or t-score, we go less. Okay. Okay, but then we have to multiply this probability by 2. Okay, good. What calculator function do I use to find this probability? Not inverse T. Not normal CDF. Not inverse norm. TCDF. Oh. I did teach you this. Yes, I did.
When?
A long time ago. Like unit 6, the front half. Yeah, I did. I swear. Lower bound, something big and negative. Upper bound, negative 7.906. Okay, and in a normal distribution, we use the parameters 0 and 1 for mean and standard deviation. But in a t-distribution, we don't use those. What do we use?
The degrees of
Degrees of freedom. And the degrees of freedom are
n minus 1.
n minus 1. So in this case, it is 9. Okay, so I'm going to pause and switch to show you on the calculator. Okay, so this is equal to 2.432 times 10 to the negative fifth, which you know is 0.1234243. It's really small. So when I compare this to alpha, what am I doing to the null? Reject. So let's write out our conclusion. With a p-value of, it's approximately 0%. The data suggests, make sure you always put that, we always hide behind the data. We just analyze data, that's it. Make sense of it. The true, and remember we're rejecting the null, so now we're kind of favoring the alternate, so we're interpreting this statement. The true mean amount of water in the bottles is not 16.9 ounces. Does he need to get repairs done? A repairman out there?
Yeah.
Yeah, get repairs. So we don't know if it's more. We don't know if they're overfilling bottles. We don't know if they're underfilling bottles. At this point, we don't really care. We just want to know if it's not working accurately, and we determine that no, it's not. Okay? That's it for notes.